Welcome to this lesson on thermochemistry. I forgot to record the lesson when I was actually doing it, so I'm just going to go through my PowerPoint and do the explanation. Okay, so thermochemistry, you're looking at enthalpy, which is heat. We need to look at the definitions because you need them for Hess's law, which is discussed in the next lesson. And then you do heating curves and calorimetry, and we'll look at all of those. So, the types of energy. If you think of the different types of energy, the ones that are important for chemistry, they're kinetic energy, that's the motion of the particles, and that's a good measure of the amount of heat they have, because the higher the temperature, the greater the kinetic energy. Also potential energy. So you have, although I've said that you've got your chemical potential energy stored in bonds, it's more that the energy is given off when bonds form, so energy is released when bonds are formed, and then you need energy to break those bonds. So saying that it's stored in the bonds is not strictly speaking correct. And then of course you've got your heat energy. So if energy is given off during a reaction, it's an exothermic reaction, and if energy is taken up, it's an endothermic. As we can see here, if your reaction mixture becomes hotter than the surroundings, that's an exothermic reaction, and the other one is endothermic. Now, the enthalpy change, as I say, enthalpy is just a fancy word for heat, is we're looking at the energy of the products compared to the energy of the reactants. So we always subtract the energy of the reactants from the products, and that gives you the amount of energy that's been removed or taken up. So has heat been given off or been taken up, or absorbed or released? So if the energy of the reactants is higher than the energy of the products, we release this amount of energy, the difference between the two, and that would be, and if you think about it, exothermic or endothermic, have a think. I hope you picked exothermic. And here the energy of the reactants is lower than the energy of the products, so we've had to add energy to get up to the products. So I hope you realize this would be an endothermic. So if it's exothermic, heat is given off, so it's the reaction has lost that heat, so it's a negative. And endothermic, the reaction has had to gain that heat from elsewhere, from the surroundings, so that's a positive value. Okay, now these definitions are important, as I say, particularly for Hess's law, which we'll do later, but really for any part of the thermochemistry. So the first one is the heat of formation, and it's shown by delta, meaning change. H is the symbol for enthalpy, and F for formation. And that definition says that if I want the heat of formation of a particular substance, then it's always for 1 mole of that substance. So that appears on the right-hand side. So if I want the enthalpy of methane, so the heat of formation of methane, I'll have 1 mole of methane on the right-hand side. On the left-hand side, it's the elements in the standard states. So methane is made of carbon and hydrogen, so you would have to have those on the left-hand side. So here's an example of the heat of formation for sulfur dioxide. So I have 1 mole of it, so there's 1 in front of the SO2 on the right-hand side, and the elements in their standard states on the left-hand side. So sulfur is a solid at room temperature and atmospheric pressure. Oxygen is a gas at room temperature. And oxygen is also the common allotrope. The other allotrope is ozone, but that's not the stable form. So we use oxygen in the gaseous form. And that's just to highlight the fact it's always 1. Heat of reaction, this is the general one. So it's always for the reaction as written. So if I had doubled this, then this would be the heat of reaction for twice the amount. Or here's an example. Heat of reaction of ammonia to make ammonia. Can you see there's a 2 in front? So if I had to do the heat of formation for ammonia, then I'd have to have a 1 in front of here, which means I'd have to have a half in front of the N2 and 1.5 in front of the H2. So the heat of formation for ammonia would be half the value of this given. So if this was, for example, the heat of reaction for this equation is written as, say, 300 kilojoules per mole, then the heat of formation would have been half of that to make 1 mole. Right, heat of combustion. This is always burning in oxygen 1 mole of the substance. So we always have on the left-hand side of the equation now 1 mole of whatever substance we're combusting plus oxygen, and on the right-hand side is the element, and is the oxide, most common one. So for carbon-based, it'll be carbon, and oxygen is carbon dioxide rather than carbon monoxide. Also, organic molecules have hydrogen, so the common oxide for that will be water. So if I burn methane, it'll be carbon dioxide and water, and so on. So here's an example of hexane. So remember it's 1, and because it's a 1, I have a fraction here. So thermochemical equations, you are allowed fractions for balancing. And that's to highlight the 1. So here you can pause the video and see if you can write the equations. And I'm just going to give the answers very soon. You just pause and make sure you can get through. Right, here are the answers. So do you notice for the heat of formation, I have to have half because I need a 1 there. Water, I need a half for oxygen because I have a 1 in front of the water. For combustion for methane, okay, the common oxides, sorry, I said methane, I meant pentane. But the heat of formation of pentane, for formation I have to have this pentane liquid on the right hand side and the elements on the left hand side. Now remember I spoke about the common allotrope for oxygen. In this case the common allotrope for carbon is graphite. So it's not diamond, it's not lonsdaleite, it's not nanotubes or so carbon fiber or whatever. It's graphite because each of them have a different energy. So graphite's the default one. And then the heat of combustion of methane, notice I also have to have a fraction in there to make sure I have a 1 in front of the methane. Right. Now there are other definitions. So you've done 3, combustion, reaction, and formation. These are the changes of state, and there's 3 of them. There's heat of fusion. Now fusion, you always think you're fusing, you're becoming a solid, but it actually is going from solid to liquid. Okay, so ice solid to liquid water. So it's the same substance, just in a different state. And it always has to be 1. Okay, vaporization is going from a liquid to a solid. And again, you have to have the 1 in front of it. And I didn't put the sublimation. That's when you go from solid to gas. Now, what that final note I've put there is your fusion and your vaporization enthalpies can be used to discuss intermolecular forces. So instead of saying the boiling point of methane is this and the boiling point of water is that, why is there this difference? And then you would go on about methane only having temporary dipole forces of attraction. I could do exactly that same question, but I could give you the delta H vap. So I could give you the delta H vap of methane is this, and the delta H vap of water is that, and you would have to then say methane has only got temporary dipole forces of attraction, whereas water has got temporary dipole forces of attraction, permanent dipole forces of attraction, and polar and hydrogen bonding, and you could explain why and so on, and then the strengths. Now, to change state, we go we draw heating curves. So you may be given a heating curve or asked about various aspects of a heating curve. So what is really happening here is you're going from a solid. So as we increasing the temperature, and the particles are still in the solid form, they're vibrating more and more and more, so that heat we're adding is going into the movement, so the temperature is increasing. Then I start breaking the forces of attraction, those intermolecular forces between the particles. Okay, so can you see that all this was a solid? Now I'm starting to break them. Okay, and so there's no change in temperature because all the energy I'm adding, because I'm adding heat all the time, but all that energy is going to breaking bonds. Remember I said forming bonds releases energy, breaking bonds requires energy. Now I'm in the liquid form, so I've broken quite a few of my intermolecular forces, so the particles and clumps of particles can move around. So as I'm increasing in heat, those particles are moving faster and faster and faster, so the temperature is increasing. So there's increasing kinetic energy because they're moving faster, and remember I said kinetic energy is a measure of the temperature. Right. And then I get to a point where the temperature doesn't change, even though I'm adding more and more energy. And that's because all that energy is being used to break the last intermolecular forces. Because to go from solid to liquid, I only need to break some of the intermolecular forces. I can still have clumps of molecules. But when I go from liquid to gas, I'm breaking all of them. And so that's what we're trying to show here, the liquids going into the gaseous phase, and here I've got totally gaseous. I'll explain this MC delta T and the MC delta T, but basically this is the heat of fusion, heat of vaporization, and you can work out the bits in between. And I'll now go to an animation which shows this. So here I've got one, and it should be on Otto. So here I've got, say I want to go from my solid, okay, I'm going to reset. So I'm going to go there. Can you see it's a solid? I'm showing, you know, the hexagonal hydrogen bonding us pattern there. And say I want to get it to a liquid, right? So those particles are still very close, but they're moving around a bit more. For 75 grams, how much energy have I heated to do that? And you can see it's 50.6. If I increase the amount, whoops, okay, if I decrease the amount of water, notice if I calculate again, it's gone down. I can do this going from, say, a solid to a gas. So can you see the gas particles are further away? And for that same, but I think previously it was about 40. If I now calculate, it's 185. So I actually break quite a few more particles to get it, sorry, I don't break particles. I break the forces between the particles. So I break quite a few more intermolecular forces to get it to the gaseous phase. So that's quite a sort of nice little interaction to see what's happening. The other one is this one. So I'm going to go here. So basically what's happening, we're heating the ice. So you can sort of see there that's how ice is being heated. Now all the energy is going into breaking some of those intermolecular forces. And then what's going to happen, I carry on heating, and that energy is going into kinetic energy. So the particles are moving faster. Now I'm breaking the intermolecular forces, and can you see it's sort of breaking up into smaller particles, and I've now into the gas phase, and the gas particles are moving faster and faster. So those are nice little interactions to see what's happening. And it's showing the sort of the heat of fusion for water. This is for joules per gram, because of course it's always got to be for a certain quantity, because the more water you have, you know, if you half fill a jug of your kettle, it's going to take shorter than if you completely fill your kettle and want to boil the water. Okay, so let's go back to the slideshow. And as I said, the heating causes the particles to gain kinetic energy. And I know from past exam papers they do want you to discuss kinetic energy. And then the fact that you're breaking the intermolecular forces. Right, this is an example of a real life thing that somebody had done. And it's quite good to note, can you see he's heating it? You don't actually see the hot plate underneath here. And it's not doing that pattern that we were expecting. Okay, it's only slightly increasing. And you notice we've still got ice, and you can notice the ice is melting. Okay, but it's increasing, but it's doing funny things here. So why is that? Think about it. We will discuss it just now. Notice we've still got ice in here and it's still doing funny things. Okay, now there's no ice left. Okay, look what's happening. It's going up in the nice line that we expected and we saw in our previous graphs. So we're expecting to see that. Notice it's wanting to start to boil. You can start seeing it's not quite boiling yet. Now it's starting to boil. And notice what's happening while I'm boiling it. Okay, there's that nice flat thing again, and we'll just stop that there. Okay, and then if you carried on, it would keep on going up. If you think about it, why do we have this not very clean curve the way we expected? And it's partly because the person recording this deliberately didn't stir the mixture. So what we're having cold spots and hot spots. Whereas if you had frantically stirred this mixture so that the temperature was even throughout, then it would have matched the heating curve that you expect more often. But it's always good to think about what's happening in practice, why isn't it matching theory, and thinking about how you could improve the practice. Okay, so that's a nice little video to see that heating curve. Now, let's look at some past exam papers. There wasn't anything on heating curves last year, but in 2014 there was. So you had to explain what was happening from A to D. So the things you had to discuss was the gain in kinetic energy as you increasing the heat. You know, with time, you're adding more energy because you're heating the system. And as you're adding more energy, the particles are moving faster, so the temperature increases. But between B and C, you're now getting to the boiling point. Okay, so you're changing from liquid. You know that that's changing from liquid to gas because you had this flat part over here. So that can't be changing from solid to liquid, because then what on earth is this bit down here for? So this is going from solid to liquid, liquid to gas. And then you have to explain about having to break all the intermolecular forces to separate the particles. Okay, and that's why the temperature doesn't increase. And then finally explain why this increases. It's again, you've broken all the intermolecular forces, so all that added heat is going as energy, kinetic energy for the particles. Right, here's one from 2012. Where it's not a heating curve, but they give you the delta H evap and fusion, and you have to talk about the intermolecular forces. So remember, level 2, you get away with just saying intermolecular forces. Level 3, you have to speak about each one and the factors that affect each type. So in this case, it's water. So you've only got one substance, but you can talk about all three, okay? And then, now notice I've said intermolecular forces here, and then I've abbreviated it, so I can continue to use the abbreviation later. Don't use an abbreviation without explaining what you mean. So you can say hydrogen bonding, and then in brackets after that H bonds, and then you can keep on using H bonds after that. But don't use H bonds straight away. Explain that H bond, you mean hydrogen bonding. Okay, so can you see I can now carry on with my abbreviations, but I had to define them first. And so these are the key points you need to know. So about breaking all the intermolecular forces. So you're going to need more energy to vaporize than to melt. Here's another one where you use the delta H VAP. Okay, so here we're looking at chloromethane and methanamine. So they give you the molar mass. So if they give you the molar mass, it's a little help to tell you, hey, when I discuss the temporary dipole forces of attraction, I need to talk about the effect of mass. That the bigger the mass, the greater the temporary dipole forces of attraction. So the chloromethane has got nearly double the mass of the methanamine, so you're going to have much stronger temporary dipole force of attraction in the chloromethane, which means you're going to need more energy to break those, so the delta H VAP is going to be more. But then, of course, I hope you realize this has got hydrogen bonding, and so those are also very strong attractions, and that's why there's not that much difference between them. This one has got very strong temporary dipole force of attraction. This one's got very strong hydrogen bonding. So they've got similar delta H VAP. Also mention, of course, that they've got permanent dipole forces of attraction because both of these are polar molecules. So remember, we talk about that. So there, I've made that statement. Molecules are polar, permanent dipole forces, and then all the bits that I have already discussed. Okay, so that was from 2009. So let's move on now to calorimetry. This is where we measure, where did we get this delta H VAP? Where did we get the delta H fusion and so on? We do it with either what we call a coffee cup calorimeter or a bomb calorimeter. Now, coffee cup calorimeter is done at constant pressure. So this is open to the atmosphere, so it'll be always atmospheric pressure. This one is in a sealed container, so the volume can't change, but the pressure can. So you tend to use a bomb calorimeter for burning things. So if you want to find the heat of combustion, you would use a bomb calorimeter. So if the substance you're burning, you put in here in an oxygen atmosphere, and any energy given off is absorbed by the water. So the more water you have, the smaller the change in temperature. I mean, if you heat a teaspoon of water over a candle for a minute, okay, that will get hot. But if you took a whole great big, 2-liter flask and held it over a candle for a minute, the temperature of the water would hardly change. So the mass of the water is very important. Okay, and the same thing here. It's still the reaction mixture that's happening in here. That heat is has to be absorbed, by something, and we tend to measure in both cases the temperature change. So this has to be as insulated as possible so we don't get any heat loss. There is an experiment that you do in 3043, which I would like you to do, because doing the experiment makes you realize where all those heat losses can occur, because there's often a question on, a student did this, got this, calculate the value that they would have got, but the theoretical values this much account for the difference. So it's good for you to be able to discuss where you could lose heat. Right. Now, a key point to remember is what is losing energy and what is gaining energy. If, for example, I'm burning a substance in here, the substance is losing the energy, so that's exothermic, and the water is gaining energy. So that is, because it's gained it, it's become positive. So when you do calorimetry questions, you're going to have to do a sign swap, and it's really all to do with because the reaction has lost that energy and the water has gained it. and you first calculate it on the water, and then you have to go to the reaction. So let's see what I mean. Okay, so first of all, you need to know the specific heat capacity, and it'll always be given to you, so you won't have to memorize anything. So with those heating curves, you saw that MC delta T, that C in that formula is the specific heat capacity. And 4.18 is for pure water, and they tend to say they use it as well for any solution. They'll always give you the units, and use the units to help you work out. If you've forgotten the formula, the units will help you remember, do I multiply by temperature, do I divide by temperature, and so on. And we'll get some examples of that. So the energy that's been lost or gained in kilojoules, there's joules, that's kilojoules, and that's the reason why we're dividing by 1,000, because we're changing from joules to kilojoules. Okay, so there's at 4.18, which is joules per gram per degree centigrade. Mass of the water, which is absorbing that energy, so that's in grams, so that cancels out the per gram over there. And the temperature change, that's in degrees centigrade, so that cancels out the degree centigrade or per degree centigrade over there. Okay, so you could also have it as Q is equal to MC delta T, and as I say, the Q for the reaction is the opposite to the calorimeter. So if the calorimeter became hot, it's because the reaction was giving off that energy. Okay. Right, so here's an example. I've taken potassium hydroxide and I've dissolved it in water, and so on and so forth. There's a whole lot of information there. What are you going to do? The best is highlight, underline something to get all those figures out there. Then make a list, and notice how specific I am. You know, I'm giving the units, I'm telling you the quantity, mass, specific heat capacity, mass of calcium hydroxide, the molar mass of calcium hydroxide. You are never given molar masses, you are expected to work them out from the given periodic table. So you can always work out molar masses. Right, so now that I've got that, I use the formula MC delta T to get my energy. So I had 100 grams of water. It's the water that's doing the absorbing. Okay, I've got the specific heat capacity given for water. So 100 grams times the specific heat capacity times the temperature change. So it went from a lower temperature to a higher temperature. So 34.7 subtract 23 is 11.7. And notice how my units cancel out, giving me an answer in joules. And so if I wanted kilojoules, I'd have to divide by 1,000. Okay. Now, notice I have a positive value from the calorimeter. So actually the reaction was exothermic. And I think it's clear that the reaction is exothermic because it's gone up in value. Okay, the temperature has gone up. Now I have to convert kilojoules to kilojoules per mole, because I didn't have 1 mole of potassium hydroxide. I was given 5.03 grams. So I have to work out how many moles have I got in 5.03 grams, and I divide it by the molar mass, get the moles, and so I can, by dividing my kilojoules by my moles, I can work out the kilojoules per mole. Right, here's another one from 2009. So again, you know, you go through, you highlight. Now I've just given an example of here that a lot of students do. They just sort of list, if they do list it, a whole lot of things. But can you work anything out from that? I mean, that's just plain confusing. So always give a context, give the units. So what substance are we referring to? What is the quantity? Is it a mass? Is it a molar mass? Is it a, you know, so on. So If you list the values like this, it immediately makes sense. You can start putting in your equations. So hopefully, if you've got the molar mass and mass, you're thinking of number of moles as big M, sorry, little m over big M. Hopefully, when you see a mass of water and specific heat capacity, whenever you see specific heat capacity, start thinking of MC delta T. Okay, and you get given two temperatures, so that's your delta T. And use your units to help you work out the equation if you've forgotten it. And then you just simply substitute. Now notice that's kilojoules, not kilojoules per mole, because I haven't got it to 1 mole yet. So I have to first work out the number of moles, divide the 10.7 by it to get the kilojoules per mole. Also notice the sign swap, because I'm going from the calorimeter and putting it back into the reaction. So if the temperature's gone up, it means I must have had an exothermic reaction. Okay, and this was from 2013, highlighted, list your values. Now this is where we've mixed two solutions together. So what happens here is you have to combine the two solutions to get your mass of water. Okay, so I've got 25 mils, and 25 mils makes 50 milliliters. You're told to assume the specific heat capacity is 4.18, so we're going to assume the density, oh, and you actually told you, sorry, the mass of the mixture is 50.0, so you've put it together like that. Then you will also need the mole ratio, because let me just see, to produce the aqueous ammonia, because sometimes it may affect what you do. So Q is equal to MC delta T. You just put in your mass of the solution that was absorbing the heat, the specific heat capacity, and you were told to assume that you can use it with the temperature change. The temperature rise has been increased. So remember, although I've got a positive value there, it's got to be eventually a negative value overall because it's been given off. Now I'm working out how much ammonium chloride are formed, and that's also why we have that mole ratio. And so the value that we have over there divided by the amount in moles gives you that final figure. Please see how I'm showing all my working. Make sure you show all your working. And then your final statement should be written there for excellence. It's always a good thing to finish on, instead of just leaving it as minus 54.3 kilojoules per mole. Go back to the question, see what they were asking, and make a statement. Okay, and I think that's where I'm going to finish. So next lesson is going to be on Hess's law. So from this, you follow on with Hess's law. So goodbye.